This conference will now be recorded.
Hello, Vinita madam.
Yes, ma'am. Shall we start, ma'am?
We can start, ma'am. Akilan sir came. HOD ma'am came.
Okay,
Hello.
ma'am. Ma'am.
Good afternoon, ma'am.
Can we start, ma'am?
HOD ma'am, we can start our program.
Start.
Okay. Good afternoon, everyone present here. And I welcome all the participants. Okay. I welcome all the participants for the today's workshop on battery management system for electric vehicles. I welcome our HOD, Dr. V. Tabilchelvi, and Dr. P. Usharani, Professor and Coordinator of this today's workshop for this event. And I heartily welcome to Mr. G. Akilan, today's speaker of this speaker. And once again, I welcome all for this today's workshop. Now, I invite our head of the department, Dr. V. Tamilchelvi, to deliver the welcome address. Ma'am, please, ma'am.
Hello, good afternoon to one and all present here. I hope all of you will be maintaining the social distancing as well as you are safe in your home, as well as you have to take care of your health. In this lockdown period, these type of topics, battery management system for electric vehicles, latest topic, it will be latest topic and extremely knowledge for the faculty members, not only the faculty members, but also for the students. So you have to enhance your knowledge by attending these kind of workshop, webinars, as well as the faculty development programming. And we have to share our knowledge to our students. And in spite of our busy schedule as well as work from home, I would like to welcome on behalf of our management department as well as the coordinators of this workshop, today's workshop, on behalf of our staff members. I would like to welcome Mr. G. Akilan, who has accepted our invitation to deliver a session on the battery management system for lithium-ion battery topic. So I would like to welcome Mr. Akilan, as well as I would like to welcome all the participants for this today's workshop. I hope you will be getting a better interaction session in this today's workshop. So once again, I welcome you all. And now you can have a brief introduction about Mr. G. Akilan by our organizer, Dr. P. Usharani, and Vinita, JC Vinita, Associate Professor, as well as Ms. S. Carbonelli, Assistant Professor. Thank you.
Thank you, ma'am. Now I invite our Professor Dr. P. Usharani to introduce Mr. G. Akilan. Ma'am, Usharani, ma'am.
Yes, ma'am. Good afternoon to all. We thank our chairman sir, our vice chairman sir, our principal sir, and HOD madam for having given the permission to conduct the today's workshop on battery management system for electric vehicles. I wish to thank Mr. Akilan for accepting our invitation. I welcome you, sir. I welcome all the participants. Mr. Akilan, he is a passionate about electric vehicles and energy storage technologies who did his UG from SRM University. As a team head, he and his team won second place in static judging for autonomous surface vehicle competition conducted by the Office of Naval Research at Virginia, USA. He has 3+ startups and industrial experience leading around 9 lithium-ion battery management system projects for electric vehicles and energy storage applications in Green Tech Motors and Center of Battery Engineering and EVs at IIT Madras. A warm welcome to all faculty members and students coming from throughout a nation and other country also. From Ethiopia, one person, one faculty member has attending now. I thank all the participants. The participants count is approximately, it has crossed 300. We have limited to 250. The states, Tamil Nadu, Pondicherry, Kerala, and AP, Telangana, Karnataka, Bihar, Madhya Pradesh, Punjab, and Maharashtra. Thank you all who have registered for our workshop. Regarding BMS, generally batteries are used for power supply or the input for your electric vehicles or hybrid electric vehicles. Why you are using battery as the power supply? As due to high energy density, long life cycle, and low pollution. Sometimes improper operations such as overcurrent, overvoltage, or overcharging and discharging will cause some issues. These issues, we have to prevent this. For that, safety and performance of batteries, we are going for BMS. BMS includes, it will measure the individual cell voltage, state of charge SOC, and state of health SOH, temperature measurement. So at the end of the two sessions, all the participants, faculty members, and the students will hope that you will gain knowledge and enhance in the field of electric vehicles. I request Mr. Akilan to hand out the section. Kindly deliver, sir.
I request all the participants to mute your audio as well as your camera because only disturbance are coming.
இந்த செவரும் தெனாவட்டும் இருந்தா ஓஹோன்னு இருக்கிற என்
Hello. Can you hear me, ma'am? Hello.
Yes, sir.
Good
I
evening,
can
good
hear
evening,
you,
Akilan.
sir.
Can you hear me, ma'am?
Yes, sir.
Can you hear me now, ma'am?
Akilan, sir. Akilan, sir.
Hello.
Are you
Yes,
in the
ma'am.
line,
Can you
sir?
hear me now?
Kindly share your PPT, sir.
All right, ma'am. You can hear my audio, right?
Yes, clearly it's coming, sir. No problem.
All right, ma'am. I'll start. Hello, everyone. Thanks for. First of all, I would like to thank R.M.D. Engineering College and Vinita ma'am and Usharani ma'am for inviting me to this faculty development program. And so today I'm going to talk about battery management systems and the electric vehicles overall architecture and so on. So before that, good afternoon, everyone, and I hope that everyone is ready and their notes. This is going to be a very good session for you to head start for your any research you wanted to start, or even you wanted to do any further research on particular topic. So let's start that. So what is a battery management? What is battery management system, and why it is required? What is the need of it? And before that, we will see like why it is required for particular electric vehicle systems and why it is very important. And this is one of the importance of systems in the overall electric vehicle system itself. So we'll see that in a further slide, and we'll at the end of this slide, I'm going to give you an overview, basic idea of battery management system, and as well as I'm going to point out the research areas where the research is still open and active, where you can participate on that. So before I get into the topic, I would just like to, share my experience and the end result of our work at IIT Madras, which we did in electric vehicles at the Center of Battery Engineering and Electric Vehicles Lab at Electrical Department. So the first thing is that we have designed and developed energy storage applications, off-grid solutions, and we deployed around 20K units for off-grid areas like Meghalaya, Odisha, Himalayan regions, and UP, Uttar Pradesh, and so on, so on. So it's still expanding, and this one of the solution which will help the people who are not having a grid solution, and which ultimately gives more expansion in their lives with with this solution of energy storage application, where we have implemented lithium-ion batteries and battery management system and maximum power transfer for solar application in one single system. Apart from that, we have deployed 10 plus electric scooties, which we have designed, the batteries which we have designed, and we have deployed in the electric vehicles, and we collaborated with Zomato, and we are doing a pilot testing around Chennai. So if you're staying in near Gindi or Velachery or somewhere around near the IIT Madras, so you can see actually if you order Zomato food from Zomato, you can see actually electric vehicles delivering food near Gindi and Velachery. So these data will help us to improve and monitor the efficiency what we built, and further improving the design and deploying in the production line. So apart from that, we also doing pilot testing around more than 15 autos from various companies. Same thing, we are doing a pilot testing of our battery packs, what we designed, battery management system. So whether the efficiency is good, is the safety being proper, and is it feasibility is good, and for Indian system, is it preferably good, or do we need to do any other innovation on top of that? So in this scenario, what people do is that anyone can use this particular auto, or you can just get book the particular auto, and you can go from point A to point B inside IIT Madras campus. So again, this will allow to get more data for improvement. So these are some end results, and we're also working on electric cars and so on, electric cars and electric buses and so on. Anyway, so why I actually shared this particular these slides I really believe that showing some end results or showing something which is being reached to people, what we are doing is actually enhances anyone to be motivated to get into research and development and so on. So anyway, so let's get into the topic. So as we said, we are going to talk about battery management system, right? So it's basically a subsystem of battery or battery which is involved in the electric vehicle or energy storage application. So before getting into the batteries, the battery management system, I just wanted to show you a rough idea. So where this particular battery, the battery management system, sits, or importance of the overall architecture of the electric vehicle. If you see here, these are the few subsystems, important subsystems of electric vehicles. In that, more important is two subsystems. One is electric motors, which you can see here on the left arrow mark, and the second most important, the most important other subsystem is battery pack. So these are the very important subsystems. Apart from that, we have other subsystems as well, but these are the two subsystems which make actually a vehicle, any vehicle, to a electric vehicle. So I would, now we know like what all things are there in the electric vehicle and what we're gonna see in that particular subsystem. So now, as we discussed, we're gonna see battery management system. Why we need the battery management system? What is the need of it? So I'll just give you a few stories from the history, from the realistic scenario, which will explain why the need of battery management system is required. So this is, I think you would have seen maybe in news or something like that, but I'm not sure how familiar everyone is, because this particular product, it's a hoverboard where you can just stand and you can just go from point A to point B, because it's very famous in the United States, but also in India, but not that famous. So what happened in the United States is that all these hoverboards started, exploding with fire, with fire. So because of this, what happened is that all the hoverboards were recalled from the manufacturers, from all the customers. So millions and millions of hoverboards were recalled and gone through what was the issue. So the issue is that the battery inside. So all these products use lithium-ion batteries, right? So what happened is that these lithium-ion batteries is very, if it is not properly monitored, these are very harmful to human beings, which can injure. Worst case scenario, it can even lead to fatal. So what happened exactly in this particular scenario is that the battery is getting heated up a lot, and due to the overcharging of particular battery pack. So which can be eliminated if the proper monitoring and systems are available. But here's few issues in the technology. And because of that, what happened, the batteries got exploded, and it became a very big mess. And if you're not aware of this particular product, and that's totally fine. But the next product which I'm going to show you, I'm 100% sure everyone would have came across in your life. That is a Note 7, a Samsung Galaxy Note 7, right? So you would have heard at least one news everywhere in your lifetime saying that it exploded somewhere. So, and it is true. A lot of phones have exploded all around the globe. And what happened is, because of this, Samsung recalled again all the phones immediately to back to manufacturer. This caused the very big loss for Samsung. Not only the loss, but as well as reputation and of the company. And apart from reputation, what happened is it injured a number of people, third-degree burns of issue for a lot of people. So all these issues are focused on one single point, that is the battery. So this battery which is there and is used is again lithium-ion battery. So what happened is that there are certain cases happen, and they found out that the insulator is not proper, and the manufacturer is not blamed for that. So again, it's what the point is that it's very dangerous. And apart from that, this is very old picture. These days, this laptops don't explode. But if you go little bit earlier, not too much, at least 8 years, 9 years behind, you can see the news of laptop explosion. So the reason for that again is lithium-ion batteries. At that time, the lithium-ion batteries were used. Again, what happened is that the monitoring system was not better at that particular system, and which led to again exploding and fire explosion for that battery, and made a lot of people injured. So why I'm saying all these, why I'm showing all these stories is that to just make you, realize that how harmful these lithium-ion batteries are, if it is not monitored and made sure it is in right condition. So what are the reasons, these explosions happen? What are the main reasons there? So there are a number of reasons which are there, more number of reasons. The very important 6 reasons are: the first thing is that very high energy density. So lithium cell batteries are packed with high energy density than any other chemistries. So that's why we moved from lead acid battery to lithium ion battery, because lead acid battery is very bulky with the same capacity if you compare to lithium ion battery, because the energy density is more in lithium ion. So the size of the battery reduces with the same capacity as compared to the lead acid battery. So with a small size of the battery can capable of packing more energy, which again leads, which is very important. People think that it's very small size, right? But the thing is that we should not consider the size. Consider what chemistry it is, and how much capacity the cell is actually packing into that particular cell. The second thing is that mechanical abuse. Let's say the puncture, if it is punctured, or if it has been going through a lot of vibration and it's punctured accidentally, a small puncture or something like that, it may cause a fire explosion. The third point is that overcharging. So this is again one more important thing. People just leave particular device charging overnight, and it again leads to thermal explosion. The fourth point is that temperature overload. If it is not properly monitored, if it is too hot or if it is too low temperature, again the lithium-ion battery can go into non-safety operating condition. The fifth one is that short circuit. So if someone is short circuiting any lithium-ion cell or battery, again it will become very dangerous to human being. And this is why you can see all the devices which is packing lithium-ion cells, any cells which will have protrusion, which you can't directly touch the two terminals, positive and negative. Anything, let's say a trimmer or anything which you see, you can't easily touch. The reason is that this is why you don't want to do with the keys or something. You don't want to just like that touch. And the sixth point is that low quality cells. This is something very interesting reason, and this is something also because why it is very interesting is that a lot of Indian companies, a lot of startups and companies, what they are doing is that they are building battery packs and for electric vehicles and energy storage applications with very low quality cells, because always India is focusing on low cost with high quality, but ultimately what's happening is that they are making sure that it is in low cost, but they are leaving the point of high quality. So what's happening is that all are imported from China, and China sells is very low quality, and then they are building the battery pack. I'm not saying that China is not having high quality, but the problem is that getting a high quality cells from China is very difficult. And second point is that if you wanted to get a high quality cells from China also, that is very high cost, right? So again, you have to decide you're going to rise up the cost or you're gonna compromise the quality. So even the low quality cells leads to explosion of the battery pack if in the worst condition. So all these 6 points leads to one theoretical physics in the particular lithium-ion cell chemistry. So what it does, all these 6 points, what I discussed is leads to a thermal runaway of the particular cell. So what is thermal runaway? So thermal runaway is nothing but if let's say that mechanical abuse, or let's say overcharging, like for example, let's take a overcharging. So you're charging your cell, overcharging your cell. So at that point, what happens is that the cell gets heated up gradually. You can see that even if you put your phone in the charge, even if you leave more than 100%, what happens is that you can feel the heat of the particular cell phone. So what it does is that it excites the electron in the lithium ion. So these excited electrons, what happens is that create more heat. And when the more heat is generated, again, this heat helps again to the excitation of electrons. So this is a cycle reaction which will lead to rise of temperature in infinite rate. So which again, what happens is that when temperature goes very beyond 120 degrees Celsius, 300 degrees Celsius, within a matter of seconds, the lithium-ion cell or the battery catches fire. So you can see in the right-hand side, the lithium-ion battery getting, catching fire due to the overcharging. So all these points which I've shown here, 6 points, leads to this kind of thermal runaway. So that is why this lithium-ion cell is very dangerous. And coming to this, even if let's say that one particular cell is having some issue, what happens is that the heat transfer, let's say you can see in the second picture, the only one cell is let's say this is the 6th point, only one cell is low quality. So what happens is if it is low quality, it heats up very fast because of the low grade and high resistance, internal resistance. We'll talk about that, internal resistance and low grade, why low grade are catching fire and so on. But ultimately, I just wanted to show you this point. So this, let's assume this second picture, the orange cell is low grade cell, and it's getting heated up a lot. And what happens is the heat is transferred to other cells as well. So when the heat is, going higher and higher, again, the electrons will, excited more and more. And what happens is that now the excited electron again helps to increase the temperature for that particular cell. Again, the cycle reaction happens and the explosion or fire catches for that particular lithium battery. So for giving you just a rough idea how much it is, I just wanted to show you here 2 comparisons. The left side, what you're seeing is a prismatic cell. This is a cell, a lithium-ion cell. Lithium phosphate is actually what I'm showing in this picture, but ultimately it's just small difference in the characteristics. So this right side is a very famous, F1 grenade. So if you see the size comparison, it's almost same, right? So almost same. But the thing is that the energy which actually can be produced by the both of it is very enormous. And if you compare it with if you compare the cell with this particular cell to the grenade, the energy which can produce by the cell is around 3 times higher than the grenade. So you can compare how much energy is packed into this particular cell. And you might be wondering what the cell is looking different, right? Because you might have always seen cell with cylindrical shape. So, but in electric vehicles, there are different packages are there, and these are the 3 type of main packages which is used in electric vehicles or energy storage application. The first one is cylindrical cell. Again, these are used in electric vehicles and applications. And the second one, what you're seeing is the prismatic cell. That's what I showed you. It's like a brick. And the third one is a pouch cell. So the pouch cell is, we know, very familiar. It's used in cell phones and other consumer electronics. Again, in electric vehicles as well, it is used. All these 3 variants of cells will come in different sizes. So it again captures different capacities for each and every cell. So this particular we use for building the battery packs for different applications. Again, these 3 type of variants have its own pros and cons. I don't want to get in deep into that, but I just wanted to make you aware that these are available, and you can dive deeper if you wanted to in time. And so coming to this cell, These are the cells used to use battery packs, right? So, for example, the cylindrical cells are used by Tesla and planning to move to prismatic. There are a lot of reasons for that, uh, cost and so on. But ultimately, this is the thing. So, for example, the Tesla battery contains around 7,000 cells in the Model S. 7,000 cells. I was showing you just one single cell, rough idea what it is going to be. 7,000 cells, you can imagine how big it is, right? So when the battery pack is getting bigger and bigger, the overall battery system gets more complex for each and every size in the battery pack. So that's why I just found this very good quote by a CEO of Mercedes. It is very relevant over here, so I thought I'll put it over here. Intelligence lies in the cell, but the complex battery system. So when I say battery system, it doesn't only contain cells or battery. It also consists of other systems, nothing but battery management system, which manages the battery overall battery. So that's why it's very, again, the point is here is the battery management system or the battery system, which gets complex for each and every application and battery pack size. So what are the main four features of lithium-ion battery management system? Shortly called BMS. We in industry so on they call it as BMS. So I'll just say BMS in future slides. So these are the four main features which makes battery management system. There are more features we'll be adding on top of it. It all preference for that particular application or by the client and so on. But ultimately, these are the very important four features for the battery management system. The first one is that safety of the battery pack. The battery management system makes sure that the safety of the battery pack is ensured in any time. There are certain cases that where the battery management system can't take the safety of the battery pack. That is only one scenario, that is puncture of the battery pack. But that we'll see how it is mitigated and so on. The second point is that long-term performance of the battery pack. And the third one is that information of the battery health and state of charge. So the BMS ensures that what is the battery percentage and how the battery is behaving and what is the battery health is. And the fourth one is that BMS ensures that secure and safe charge and discharge control. And make sure that you note it down or just have it in your mind, these 4 points. So we're going to see how these four features are achieved by various techniques and parameters in further slides. So main 4 blocks make sure that the 4 features have been satisfied. The first one is that sensor input. Second is process the data, whatever the sensors capture the data and it process that particular data. And then third one is the actuation. So the actuation makes sure that it cuts off the power supply or it does few scenarios, few functions where to close or open the particular current path. The fourth one is that communication to the outer world. When I say outer world, that is nothing but from battery pack to other subsystems of electric vehicles. When I like motors and vehicle control units. I'll discuss all the importance. The communication is more important, and people think that communication is not that important, but communication is one of the very important thing in this particular block. We will see each and every block in detail in upcoming slides. So first block, sensor inputs. These are the you can see here 6 parameters we need to make sure all the 4 features are satisfied. ultimately, we just need three important data. The first thing is that cell voltage and battery voltage. I mean, if, you can just calculate the battery voltage by just calculating the cell voltage. We'll see that later. Ultimately, we just need cell voltage, current, charge and discharge current, and third one is temperature, battery pack temperature. These are the three important parameters we need to satisfy the four features of the BMS. And other, parameters, what you're seeing in the 6 points here under the sensor input, also needed, but not very important, but will help for ensuring more safe system. For example, battery ambient temperature, battery voltage. Coming to processors, we use controllers, processors, and so on. Right? Every different architecture uses different controllers and different processors. Actuation generally relays, contactors, and MOSFETs. Communication protocols, we have like RS-485, CAN, SPI, I2C. Again, we'll dive deeper into all these particular points. I just wanted to make sure that you have a clear idea of what we're going to see next. So next we'll see a rough BMS block diagram. This is a very interesting one. Here you can see four architectures. These four architectures becomes more complex and complex when the battery pack size increases. The first one, what you're seeing, that leftmost architecture is a very simpler one because it's just smaller lead acid battery, right? It's just having an acid battery and battery sensor and the communication. It's just IVN is nothing but in-vehicle network. It just mentions that vehicle communication vehicle communication in the architecture. The second one is that 14-volt lithium-ion cell, lithium-ion BMS. I mean, you might be wondering where these 14-volt lithium-ion BMS are all used. These are used in starter batteries, like when you're starting the car, right? Or when you're starting the electric scooter or something, or electric vehicle. The starting is being done by these kind of batteries, 14-volt, 12-volt batteries. So these are the scenarios where this 14-volt lithium-ion BMS are used. Again, you can see here battery. You can see here block diagrams. Battery cell controller basically just fetches all the battery voltage or the cell voltage, what I've discussed in the previous slide. And then the MCU is there, microcontroller, which processes the data, and it just gives functional safety SBC. It's just control. I mean, it's a driver for MOSFET and so on, which I again explained the previous slide. Actuation. This is actuation, and this is the communication. This is the 48-volt lithium-ion BMS. Again, you can see more blocks again added over here because this is 48-volt system. These are generally used in two-wheelers and three-wheelers, especially in scooties and autos. Especially, so you can see here again battery cell controller, I think, but read cell voltages. I'll get into this deeper again. What is mean by battery cell controller and so on, ASC, that especially ASC, but just make sure, have it in mind that it just takes the cell voltage. Isolation communication, again, for safety purposes, as I said, again, the more complex architecture. Microcontroller, again, actuation driver and communication. And the last architecture you can see, this is a more complex architecture than any other architecture which we have seen. This is nothing but for car. It will be again bigger, but this is just a simpler architecture. You can see here high voltage battery and the cell AC is here, isolated communication, microcontroller, driver, and so on. Again, you can see here switches, pre-charge, cooling systems, high voltage battery connectors, load switching. There are two MCUs to make sure that the data are right. Even one microcontroller is dead, the other microcontroller can carry on. So they have two microcontrollers to make sure the safety is ensured. And you can see here the controllers and the communication platform over here. So you can realize now, as you go further and further, the architecture is bigger. So let's get into a simpler architecture for a BMS. This is for two-wheeler BMS. This as we saw in the 48-volt lithium-ion BMS. This will give you a rough idea how the overall architecture looks like. This is the Class C architecture, which gives a rough idea what all subsystems involved in the overall architecture. So you can see here, this is the battery pack, and there's a fuse. Here the relay and or the MOSFET, and the driver over here, and the battery cell controller, which is nothing but AFE, which takes the cell voltages. And this is a current sensor, and this is a microcontroller. Again, they have used two microcontrollers. This might be for cars, but ultimately not required for two-wheeler. And this is power supply from the battery pack to the logic level, and as well as you can see here communication. And one more thing is that why I said two microcontrollers not required in this particular architecture for two-wheelers. As I said, the big battery packs, the standards requires more safety for that particular product. So you have to ensure the product level safety. So I'll explain detail when the safety comes into the picture, how the technology or the design aspects get very complex. That's why here two MCUs are there. So coming to the first parameter, that is the cell voltage, what I said very important, right? So how it has been acquired is through analog front end. So analog front end is nothing but integrated circuit, which is a very important integrated circuit in the system because you can't measure multiple cell voltages with just microcontroller. The microcontroller can't handle the overall the reference voltage. For example, so you can see here, this is the internal architecture of the Texas Instruments AFE. So they have different type of AFEs in the market, Texas Instruments, NXP, and ADI, and so on and so on. They have different architecture of their own, but I just wanted to show you this just for in case you wanted to get into deeper. And ultimately, the important point is here, I wanted to ensure is that you can see here, these are the multiple inputs of cell voltages. Let's say that ultimately, if you wanted to make a battery pack, you wanted to put the cells in series and parallel. You will be putting the cells in series, 10 cells or 15 cells or hundreds of cells, you will put it in series to make a battery pack. To measure all the cell voltages, you will take individual wire from the cells to get the cell voltage of the particular cells. So all the cell voltages will be calculated like that, and then it will be given input to this particular IC, and then it will read the data and give us a digital output to a microcontroller. These inputs are analog reading, and the output will be digital reading. And this only not contains the cell voltage reading, but also other applications like safety features and communication and all small features will be inbuilt in this particular IC. The application, the features will vary to different manufacturers again. You can see here that these are the cells, individual cells, which connected together to make us a battery pack. And you can see here it is given to this particular input of the particular IC. And here, very important thing. You can see here top group, middle group, and bottom group. Why? Because this is why AFEs are used. The main reason. What happens this top group is, let's say that if you're having 5 cells, that particular 5 cells are holded as one single block, and the overall voltage of the 5 cells is going to be 20 volt or something. And this reference is kept different, and this reference is kept different, and the third group is reference is kept different. So because of this, you can have multiple cells in series and can read by one single AFE. And if you wanted to challenge yourself, you just try to do your homework, how you will read 10 cells in series with a normal microcontroller. and you can easily find the answer why AC is very important. You can know the point if you want it, and if you're not understanding this particular point. So now with this help of AC, we got the input input cell voltages. We know the cell voltages of the overall battery pack. Now if we add all the cell voltages, we will get the battery pack voltage as well. So with this, using AC, we got the first parameter very easily. Now, when I talk about number of series of cells which is used to plug into the AC, there are different type of topologies to do this particular type of connecting the cell voltages to the AC. The main important issue is the AC can only the AC in the market right now can only measure 13 to 16 cells in series. You can't measure more than 16 cells or 15 cells in series. The in particular manufacturer right now what they have. Let's assume if only can measure 16 cells with the AC, that means one person can make only 67-volt battery pack, but he needs 100-volt battery pack or 200-volt battery pack or 80-volt battery pack or 90-volt battery pack, which actually required for cars, buses and so on. One single AC can actually, if you only make with 16 cells in series, it easily can be suited for two-wheelers and so on, because two-wheelers and three-wheelers will use mostly in 48-volt and 72-volt, which actually can be achieved with single AC. What if we can go more than that? So in that case, the BMS topology comes into the picture. So here I'm going to show you 4 basic architectures which is mainly used in the industry. Again, in this 2 important architecture widely used are master slave and modular. We'll come to that. I just want to show you first one, master slave, because this architecture is very famous. Everywhere is used, Tesla, Nissan, and so on. So the first thing is that when you see a slave or battery controller, so the slave contains each ASC. So each ASC can read 15 cells or 16 cells. So now we can read more than 16 cells, and all the slaves will give the data to the controller. Now controller will have all the cell data. So let's assume here there are 4 slaves. Let's say 4 slaves one slave is reading 15 cells. That means the 4 slaves can read now 60 cells. So now the BMS controller have 60 cells in series data. So that means 60 cells means this is 250 volts battery pack. So with this particular configuration, one can achieve bigger battery packs. Again, we have another type of architecture, something called modular one. So this is if you see here, these are the cells which you see here, and these are battery controllers. When you see here battery controller block, 4 battery controller block is there. Each battery controller is having AC and a controller. So each battery pack will read the AC, and the AC will send the data to controller, and the controller will again pass the data to another controller, and it will keep going on. And one single controller will hold all the data and will be given to centralized unit. So these type of architectures are used mainly in energy storage applications. When you are building a battery pack like megawatt and kilowatt, megawatt are that big capacity, these kind of architecture is easy. Why? The reason is you can actually put it as a module, big module. You can add or remove from this particular module. Let's say you have 1 megawatt of energy storage, battery pack, and you want to make it as 1.2 megawatt. Now you can actually add 0.2 megawatt of module with this battery controller on top of that, and you can just add to this particular module, and it will become 1.2 module. So it is very easier to manage the data with this particular architecture. And coming to the centralized architecture, this is what we saw for two-wheelers. Like one single AFE, it just reads all the 15 cells and just sends to the controller and takes the decision. Again, if you see the fourth one is a distributed one. The distributed architecture is a very old architecture. It is not very feasible, and I'll let you know why. And it's also like very costly also. Each and every cell will have its small analog reading IC, and then these analog reading IC will send the data to the controller. So that means if you are going to have 15 cells, you will be designing 15 analog input reading circuits for each and every cell, which is going to increase the cost and also going to make it more complicated. So these are the older architecture which is not used much in any way. These type of architectures are used especially for very smaller systems and energy storage applications. Even though that is also being overcome by different architectures. So as we saw the architectures now, we'll go to the next parameter. So we already saw the cell voltages, how cell voltages and how battery pack voltage is measured, and how the cell measurement topologies are made. And coming to the second parameter, important parameter is current. So we need to know the current to make the lot of decisions, especially the charge current and discharge current. So there are different ways of measuring the currents, but very widely used and important current measuring techniques. Two techniques are used in electric vehicle and energy storage applications. The first one is that shunt, and the second one is that Hall effect. So we'll see about shunt type. The shunt type is nothing but a resistor, a normal resistor. You can see here. So what we'll do here is that let's assume that the stick trace is actually the charge and discharge path of the battery. The current flows through this path. So in this path, we'll put this resistor in series. This resistor will be very less, like 0.5 milliohm, 0.1 milliohm, something like that. Very, very, very small value. So why we gonna do this? Because how we gonna measure through this is because we'll measure the voltage drop across this resistor when the current flows, and we will read the particular voltage drop, and then we can easily calculate how much current is flowing, because we know the resistor value, we know the voltage drop, and using this we know the overall voltage of the battery pack. So we know by Ohm's law, V is equal to IR, we can easily measure the I using R and D. And people can ask, if the resistor value is very small, the voltage drop is also going to be very small. Yes, ultimately the voltage drop also is going to be very small. So what people do is generally that they put amplifier and then they will enhance the particular analog signal to the controller to process the data. So that's how it is done. And again, this particular technique is having its own pros and cons. Pro is that it's very easy to implement, very cheap, and it's used widely in small applications. The con of the particular technique is that it can't be used for bigger applications. It can't be used for more than 5 kilowatt of battery pack. Why? Because if you take a two-wheeler or three-wheeler, especially scooties, autos, or rickshaws, the continuous current is going to be around 25 to 30 amps, and maximum peak will be like 60 to 90 amps peak for a few seconds. And for cars, buses, the continuous current is going to be 150 amps, 300 amps, something like that, buses and cars. And the peak is going to be 600 amps for a few seconds. So the voltage drop will be very higher, even though if the resistance is very small. So what's going to happen is that the more voltage drop and the power dissipation, the voltage drop will actually transfer as a power power dissipation, and this power dissipation will again is nothing but heat. The heat will be there in the overall PCB again, which will impact the overall system performance, and as well as you're going to lose a lot of energy from the battery pack. It's very bad, right? So these are the cons. So to overcome this particular con for the bigger battery packs, like especially for cars and buses and so on, tractors, trains and so on, people usually use Hall effect sensors. So as everyone would know, Hall effect sensor, which usually uses electromagnetic radiation to read the current flow. Generally, they're used for bigger application. The wire is passed through a particular current sensor, and the output is taken as a readings. So these for example, to say very easily to get it, if you would have seen clamp meter, it uses the same technique to measure the current for AC and DC. So this is how, in this case, there is no resistance, there is no power dissipation, and so on. So because of that, very high amount of current can be easily measured. But the con for this particular technique is that because of the electromagnetic and the magnetic, there will be an error when small amount of current is being flown. There is basically accuracy issue in this particular technique, and ultimately these error has been eliminated due to that small amount of current is not a big deal in the very big application. That's why in some applications they eliminate this particular errors, but to overcome these errors, other techniques also there to implement other techniques on addition on top of this, only to read the smaller accuracy. So we know the second parameter now, and that is that current, how the current is measured. The third, the last parameter is temperature, battery pack temperature and the ambient temperature. So these temperatures are measured very easily just with normal temperature sensors, especially what is used is in the market is NTC or PTC, especially NTC, negative coefficient temperature sensor. The reason being is that it's very cheaper and it's very reliable. So because of that, these kind of sensors are used just to measure the battery temperatures. So we got all the three important parameters to satisfy the features. So we'll move on to the next part, how all these parameters are used to satisfy the four features. So now I just wanted to move on to the next stage. If all these three parameters, what I've shown, if exceeds certain threshold, that means it is not good for the battery. That is why. So that there is something called safety area, operating area for lithium-ion battery. So lithium-ion battery is having its own characteristics. So it has to be monitored and function with various operating area to ensure the safety and the long performance of the battery pack. So you can see here the overall characteristics and how it is used. So if you can see here, the green area or the orange area is usable area of the battery pack, and the yellow and red is not very good area to operate the cell for any application. If you operate in that particular region, it is again, it's going to be unstable and it's going to be dangerous, and it might also go for thermal runaway, and ultimately catches fire, the lithium-ion battery catches fire. So you can see here that these area is called, generally under voltage, cell under voltage. This is green area is cell over voltage, and this is SOC. The orange area is SOC. SOC is nothing but state of charge of the particular battery pack. Because we're going to use only this particular energy of the battery pack, so we call it as state of charge. So the overall battery pack capacity is going to be different, and what the capacity we're going to use is different. So that's why we give a different term for that. And this is deeper depth discharge, and so this in this area we are not going to use. Again, this again leads to short battery life, and also even catching fire if you're charging when the battery is in very less charge. So using this, we all know that cell voltage, and then we make sure that it is operated in this particular region. And this particular, to make sure the safety operating area is being carried out in this particular graph, the cell voltages and the battery voltages parameters is used. And the second parameter, the current, let's assume that the vehicle is got stuck in a pothole, an electric car, and you are trying to get out of the car very fast, and you are keep on accelerating, and it's not coming out. So what's going to happen at that point is that the motor is going to demand huge amount of over because the car needed that much, the motor needed that much amount of torque to overcome that pothole. So what happens in this case is that the motor will demand more current to satisfy the torque required. So what happens is this, again, the battery will give the amount of current, a huge amount of current will be given to the motor. Let's assume the battery pack only can provide 100 amps, but the motor is asking for 250 amps for almost 10 seconds or even more than that. If there is no monitor, and the battery pack will just deliver the current. And if it is happening like that, even though the battery pack is not able to do that, the battery pack is going to catch fire very easily due to thermal runaway. The more current goes out, and the temperature will rise, and thermal runaway will happen. And we'll see how these all happens in the later slides. But these are the reasons. That's why what happens is that when the current goes higher than certain threshold, we'll cut off the output to the load. So that's where the second parameter comes into the use. The third parameter is temperature. Again, if the car is going in the desert, or it's been in sun for a very longer time, or even some fault is occurring like under voltage or over voltage, or the current is being drawn higher or charged very higher, or overcharging, or anything happens, the first thing what we saw is that thermal runaway will happen, right? So thermal runaway is nothing but the temperature increase. So the temperature is red, and then immediately we'll cut off the load to the we'll cut off the satisfaction to the load, or we'll cut off the charging input to the battery. So we won't do anything with the battery, so that the battery will cool down and then come into the safe operating area, and then we can start using the battery again. So this is how the three parameters used to make sure that the battery is used in safety operating area. So these are the 16 basic faults will occur in the battery management system if it is operating out of safety operating area. First one is cell over voltage, battery pack over voltage, then cell under voltage. We saw that in previous slide. If it is cell voltage is very low, it is again a fault. Pack under voltage, over current during charge protection, over current during discharge protection, over temperature during charge protection, over temperature during discharge protection, and so on and so on. Short circuit protection. Short circuit protection is very easy. I have been discussing in previous slides. Basically, what happens exactly in short circuit protection is that when you short the both positive and negative of the battery pack, the huge amount of current is going to be flown through the battery pack, right? So what happens at that point is that we sense the current, and immediately we'll cut off the particular path immediately in nanoseconds, microseconds. Because of this, the short circuit will be protected. So there won't be any load to output. Even if you short, there won't be a short in battery pack. That's what we prevent. There are multiple techniques, but we'll come to that later. And next one is that not connected or unconnected or not detected temperature wire detection. This is something interesting. So let's say that the temperature sensor is not properly plugged in or something, or due to vibration in the road, the wires came out or something. The readings will be not properly registered, and again that will lead to faults, and it will lead to again thermal runaway or any fault we don't know. So it's a risky situation. So this also will be raised as a fault. And communication failure detection, if the communication is something is not happening or something, that would be again a fault. Vehicle roading detection and vehicle crash detection, all of these faults. In this case, we will completely cut off the charge and discharge to the battery pack, in between the battery pack and the load. So the battery pack will sit idle in this particular situation. And whenever the faults are recovered, then we will start the function of the battery. Then the battery will be ready to satisfy the load or charge the battery pack. So coming to the long-term performance of the battery pack. So we have seen already so long term of we have already seen the safety of the battery pack, how the safety of the battery pack is being carried out. The next one is that what I've discussed in the 4 features is long-term performance of the battery pack. So how the long-term performance of the battery pack is achieved through battery management system. So this is achieved something called a technique called cell balancing. So there are 2 types of cell balancing there. Passive cell balancing and the active cell balancing, which is widely used. There are other techniques as well. These are the very effective and widely used techniques. But before moving on to these type of techniques, we'll see what is cell balancing and why it is required and how it will help for longer battery pack performance. So before getting into that, why the need of this? Because there are 3 reasons why the cell balancing is required. The first thing is that internal resistance of the cell. The second one is that cell discharge leakage current, and the third one is actual SOC. So I'll come to the first reason, internal cell resistance. So what happens is that when the millions and millions of cells are being manufactured by the manufacturer, won't be the same value. Each and every cell will have its own internal resistance. So you can see in the right side picture, this is the cell model, electrical model. So in this you can see impedance and internal resistance and so on, so on. So every material will have impedance and internal resistance, right? So like that, the cell is also will be having internal resistance with respect to the material what they are using. So because of this, what happens, each and every internal resistance varies in a smaller variation, 0.5% to 0.2% between different cells in the manufacturing line. Even though if it is a very big manufacturer like Panasonic and Sony or so on, there will be a variation between 2 different cells. There won't be any identical cells will be manufactured. This is because of quality insurance, and as well it's very difficult to do that. It will cost very high amount of money economic wise, and also it doesn't make any sense as financial or commercial way. So because of this, the internal resistance will vary small by each and every percentage. So we'll see how this internal resistance is going to affect the overall performance of battery pack. But I'll come to the second point is self-discharge leakage current. So because of this internal resistance, what's going to happen is that there will be a small leakage current will be there with respect to the internal resistance of the cell. That's why if you leave any cell for a very longer time, if you come back after 3 years, 2 years, or even after some time, and the cell voltage will be less, even though if you're not using it at all. The reason is this is the reason. And the third one is actually SOC. The actual SOC is that the capacity what we're going to use from the battery pack. So I said again, the manufacturer is not going to be identical. The SOC also is going to be different. So all these things will lead battery pack will be going, going to be make the battery pack less efficient when the day passes throughout the year or life cycle. Let's assume I'll show you a demonstration how these three parameters are going to affect the cell. Let's assume the first top row A column is battery pack where 10 cells are in series. So all these cells will have different internal resistance, small internal resistance. Because of that, there will be a small breakage current as well. And also what happens is that when the load is connected, let's assume that this particular A battery pack is being connected to the load. When the load is being demanding some current, all the cells are going to individually give some amount of current to satisfy the overall power consumption or energy consumption of the load. So in this case, you can see the third cell and the seventh cell, few cells are in different voltages. The reason being is because of the internal cell voltage and the leakage current and so on. So in this case, because of this, what's going to happen is that when the let's say that all the cells, let's assume only we have three cells, cell 1, cell 2, cell 3 for simplicity. This is one single battery pack and this is connected to the load. So now what's going to happen is that cell 1 and cell 2 is going to give let's say 1 ampere to satisfy a load. Each cell is going to give 1 ampere because it's almost same voltage as well. But the cell 3 will give 1.4 ampere to satisfy the load. So why the reason is because the voltage is very less compared to the cell 1 and cell 2. Why? Because it's just normal Ohm's law. Because let's assume that the power requirement has to be satisfied by required by the load. Let's assume that because cell 3 is having 3.2 volts or something, then when the power is required, the cell has to be provide the same amount of power like cell 1 and cell 2 is giving out. So when the cell voltage is very less, the cell 3 can be done to compensate cell 1 and cell 2 is that increase the current output of the particular cell to compensate the same amount of power is being given out by cell 1 and cell 2. Because of that, what's going to happen is that cell voltage 3 is going to be depleted faster than cell 1 and cell 2. So because of that, what's going to happen is that the cell 3 will go completely down. It will completely go down, and because of that, what's going to happen is that there will be a open circuit in the overall battery pack now, and there will be a very weak connection between cell 2 and cell 4, and so on. And because the overall battery pack will be can't be used in full manner. Because of that, what's going to happen is the efficiency also will decrease by day, and one particular point of day, the overall battery pack can't be used because of one single cell. So to avoid this, we're going to do something called cell balancing. Cell balancing is nothing but we're going to make sure that, like how in the column B, we're going to make sure that all the cell voltages are going to be in the same voltage so that this particular issue is not going to happen. All the cell voltage will give same amount of current to satisfy the overall power requirement of the load. So what's going to happen is that we're going to do cell balancing from each and every cell. Let's take passive cell balancing. Let's assume this particular, again, we'll assume cell 1, cell 2, cell 3, cell 4 as a battery pack for simplicity. In this case, how the passive cell balancing is done is we're going to deplete cell 1, cell 2, and cell 4 to cell 3 voltage. We're going to deplete. How we're going to do is we're going to deplete the each cell, we're going to discharge the current of each and every cell through a resistor. And then we're going to make sure that the cell 1, cell 2, and cell 4 are same voltage as cell 3. Because in this case, if once the cell balancing is done, it's going to be the same voltage. Yes, of course, we're going to lose some amount of energy out of the battery pack, but ultimately, for the longer run, the battery pack is going to be giving more efficiency if we do cell balancing. And this is a passive cell balancing. And the second is the active cell balancing. In the same unit, cell 1, cell 2, cell 3, and cell 4, what we're going to do is that we're going to charge the cell 3 battery from cell 1, cell 2, and cell 4 to same level as cell 1, cell 2, and cell 4. In this case, what's going to happen is, again, it's going to be the same level of the voltage, but we are not going to lose any energy from the battery pack. And again, here, the passive and active is having its own pros and cons. The pro point of the passive balancing is very easy to implement and very cost effective. And the con of the passive balancing is that we're going to lose some energy consumption of the battery pack that's going to be there. So in this case, if we are going to lose some energy, when the battery pack has become very bigger and bigger, even the small amount of energy from each and every cell matters. And if you're going to consider or calculate the overall battery pack, then the energy consumed while the cell balancing is going to be very huge with respect to with respect to the battery capacity. So this is going to be a very big issue, efficiency issue when it comes to very bigger battery packs. So this is a very con of passive balancing. So because of this con, what's going to happen is that these passive balancing are used in smaller battery packs, like below 5 kilowatt battery packs, like 2-wheelers, 3-wheelers, autos, e-rickshaws, scooties, cycles, small energy storage applications, 1 kilowatt or something like that. Even though if a small amount of energy is drawn, the cost which we are putting is very less for the electronics. So because of that, we're going to save a lot of amount of money, and we're going to increase the efficiency on the performance of the battery pack. So the active cell balancing is very, very much sensible when we consider for very big battery packs. These are used for cars and buses, active cell balancing. So generally, how the cell balancing are used? Carried out through electronics. So I'm going to put here in the right-hand side picture, you can see a MOSFET and the cell balancing resistor. So when the particular cell has to be balanced, so what we will do is, let's say that this particular cell has to balance the top cell. We will just switch on the MOSFET here in between this. Let's say the second one, the path is clear here. The second cell bottom cell has to be balanced. All we do is that this MOSFET is turned on, and the current will pass through this bleeding resistor. The R balance resistor is the balancing resistor. The current will pass through it and will go back to the negative of the battery cell. So like this, what's going to happen? The cell is going to deplete the current through the resistor. So this is how the passive balancing is done. The similar way, the active cell balancing is also done. Ultimately, this active cell balancing is way more complex. I don't want to jump into that, but I hope this will give a good idea. And one more interesting topic is that people ask me very frequently. That's why I included this slide. Why can't we, let's say that if one particular cell is having bad internal resistance, why can't we just remove that and replace it? And this also happens in everyone's life, most of one's life. If you could have came across certain scenarios where people say that if the battery pack in laptops goes bad, all people say is that don't buy a new one. You just remove that and check the one particular cell and change it. Everything will work fine. That's what people say, and it works. And this is the reason. And people say that, and it can't be done in electric vehicle battery packs, or even in consumer markets, like it is all sealed now. It can't be done. It is for various reasons. Safety, it's for safety reasons as well as for economic reasons. People don't want it to remove, and they want to change them by themselves because it's very dangerous. And also, second thing is that the manufacturer is losing money because people have to go back and buy new battery, right? That's going to be add up value to the company. So these are the various reasons why they do it. And nowadays, the electric vehicle, you can't just remove that one particular cell and you can't replace that particular cell or a module. The reason is it's packed very close, and the mechanical design is very compact, and you can't even remove very easily. The reason being is that the vibration. So the automotives handles a lot of vibration, 10G, 8G, 8G, 7G, something like that. So because of these vibrations, the battery pack should be very compact. There should not be any vibration impact should be happening in the battery pack. So what they do is that they design accordingly so that the battery pack is very compact. So you can even see this top right corner, the cells are being stick together with very strong adhesive, so you can't even take out just like that. And also the cells are being put in series with nickel strips, which is welded, and it's very difficult to take out the particular cell. So because of this, even one cell goes wrong, or if it is not balanced properly for a longer period of time, the whole battery pack becomes waste, and you can't be used for properly. So that's why these are cell balancing is very important topic, and you can check a lot about active balancing and other techniques as well, and to go on further research. So now we got the idea how the long-term performance of the battery pack is being carried out through cell balancing. Third one is next is that BMS control. This is going to be the charge and discharge control feature of the particular battery management system. It is done through BMS control. The main three control systems of battery management system is charge, discharge system, and cooling system control and external signal. The cooling system is a very big topic. Mr. Siddesh will take that particular topic tomorrow, thermal management system. So ultimately, the battery management system is also responsible for that system, is how it's going to be carried out and so on. The external signals, let's say that some external signals has to be given out or for vehicle control unit or ignition and so on. All these controls are carried out by the battery management system. Let's come to charge and discharge. It's very important, right? So the battery management system not only makes sure that safe charge and safe discharge, it also does secure charge and discharge. We'll come to that, what is meant by secure charge and discharge. So the main two important components used for charge and discharge control is MOSFETs and contactors. Smaller applications, the MOSFETs are used, and for bigger applications, the contactors are used, like cars, buses, and so on. And the MOSFETs are the pro of the MOSFET is that it's very small, it's very compact. But the con of the MOSFET is that it's complicated, implementing in the system when compared to contactors. And that's why the contactors very comes in handy for cars and buses. When the vehicle becomes bigger and bigger, as I said, the battery pack also becomes bigger. Because of this, what happens is that the manufacturers have to be very careful designing their system. So because of this, something there is called functional safety design. So whenever the particular system is threatened to human life, let's say that particular design is capable of taking a human life if it is not properly functioning, then that particular system is designed with respect to functional safety guidelines. So these are the complexity involved, and you can further check on functional safety guideline ISO 26262 for automotives. These are the guidelines especially used for automotive safe design. So in this case, it's very complicated. You have to make sure that the guideline is followed. So what happens is that in that case, they don't want to choose MOSFETs, even though there are very high power MOSFETs. It's complicated. So with contactors, it's very easy to implement and also can carry very high amount of current in a very easy way. So that's why contactors in very high power relays are used for cars and buses and so on. Coming to charge and discharge topologies, there are few topologies even coming to charge and discharge. So if you see charge and discharge, most of the people are not aware about this thing, is that when the battery pack is inside the vehicle, when you're charging the vehicle, I mean the current path from the battery pack to the load and the current path from the charger to the battery pack is same. The path is same, and because of this, the topology is differing, and because each topology is going to give different pros and cons. We'll see that what are those topologies. So there are main two topologies are there. The first thing is that high side switching and low side switching. So before going into that, I just wanted to show this particular small diagram over here. As you see, this is the battery and this is the load. This side is the load. As you can see, the current path to the load and the charge is going to be the same path. So because of this, we need two type of charge topologies. The first thing is that low side topology, low side switching topology. And I'll show you why important the low side topology and how this is widely used in two-wheelers and scooties and so on, smaller applications. The pro of low side switching is that it's very easy to implement and low cost and so on. And the con of this is that it compromises the safety of the overall system. When it comes to the high side switching, they use the pro of the high side switching is that it's very safe, and also that the con of the high side switching is that the more amount of cost is being shelled for that particular topology. We'll see that later what exactly goes on in this. And few cases very high level safety is required, then both the topologies are used at the same time to ensure high level safety of the product. So here in the right diagram, you can see this is low side topology. How I can say low side topology? Nothing but the cutoff MOSFETs are here in low side. Low side is nothing but in the ground. When I say in high side, nothing but the MOSFETs will be in the positive side of the path. This is the difference between the two topologies. The complexity comes in how the MOSFETs will be driven in the high side and the low side. Coming to the MOSFET switching profiles. So here you can see that there are two MOSFETs are there. I said that whenever there are 16 here, the 16 faults occurs, there will be a cutoff. That cutoff is being done by these two MOSFETs or two contactors or so on. So again, people can ask why there are two MOSFETs. Even one single switch is enough to just cut off and on the particular path. Here there are two switches are there, and this is very important. I'm going to explain why this is required, and also it can relate to the topologies what I've shown here. And before that, I just wanted to show you basic four concepts over here. For example, let's say that there is no fault at all. Then what's going to happen is both the MOSFETs are going to on, and the load is going to be satisfied by the battery, or the battery can be charged directly to the directly from the charger. The second is under voltage, pack under voltage. And this case, what's going to happen is that the MOSFET switching is going to be a little different, and pack over voltage, again, the switching is going to be different. And when the complete fault any other fault occurs, like over voltage, short circuit, or something like that, both the MOSFETs will cut off completely to make sure that no current is being passed to the load. So what? Just excuse me. I'll just have some water. So yes, why I'm showing you is that for all the faults, both the MOSFETs will be off. Only for two faults, the MOSFET will be differently on. And why the reason is that, let's assume a scenario. When the battery pack over voltage fault has happened, let's say that you charge completely and you are still charging more than the battery pack voltage actually is. So at that particular scenario, what's going to happen is that in that case, you don't want to charge further, but you want to discharge the battery pack. So in this case, how that particular scenario is going to be detected, whether the battery pack is going to be charged or discharged. We don't know how it's going to happen. So in this case, to make it detect that whether the battery pack is going to be charging or discharging, what we're going to do is we're going to switch off the charge MOSFET and discharge MOSFET. The two MOSFETs are put together in such a way that, let's say that in this case, the battery pack is discharged. So what happens, the current will flow. And as you see, the discharge MOSFET is on. This is the discharge and this is charge. And in this case, the charge MOSFET is off, but still it goes through the diode, and then the discharge MOSFET is on. Then the current will pass through the sense resistor, the current sense resistor, and then it will go back to the battery. In this millisecond, we'll come to know the current direction, and once the current direction is being sensed, we'll immediately switch on both the MOSFETs, and the battery can discharge very easily. Let's consider the scenario under voltage. Under voltage, similar way, but in this case, we're going to switch on the charge MOSFET on, discharge MOSFET off. Under voltage, that means the battery is very low voltage. It should not don't want to go for deep discharge. So what we're going to do is that we're going to switch on only charge MOSFET. Again, you can see here, let's say that we are charging the battery, the current is going to be like this, and going through the current resistor, again through the MOSFET diode, and then it's going to charge MOSFET. In this case, again, we're going to sense the current direction and immediately we'll switch on. If this scenario is not going to happen, then we will immediately cut off both the MOSFETs to ensure that any further non-operating condition is carried out. So as we saw, now the charge and discharge control we have seen. Now coming to the information of the battery health and state of charge. So this is very important topic in overall slide. The reason being is that this particular topic is very highly active in research. People are still doing research on this particular topic.
செல்போனு அலறுது ரெண்டு மூணு நாளா இந்த ஒரு வாரமா நிறைய ஒரே நேரத்துல நிறைய பண்ணணும்ல.
So what exactly the information of the battery health and state of charge is carried out here? The first thing is that we need to know the battery pack voltage measurement. We need to know what is the overall battery pack voltage, and as well as what is the health of the battery pack. Let's assume that you are going in an electric vehicle and you want to know how much kilometer you can go with respect to the charge of the battery pack. So, and these are done with two particular techniques. We have to know all these information. The two techniques are that battery pack voltage based measurement, and the second one is Coulomb counting. The first one is that battery pack voltage measurement. So this is very simplistic method and very easy to implement. These kind of techniques we would have seen in everyday day-to-day life technologies. For example, LED lights, your power banks. Let's say you have a power bank and there will be LED indicators, right? So it will letting you know how much charge is there. So it's basically it just reads the voltage of the battery pack, and then it shows how much charge is there. And the second one is that coulomb counting. I'll come to that later. But we can't use only voltage based measurement in electric vehicles. The reason being is that in electric vehicles, what's happening is that the load is going to be very dynamic. The current delivery is going to be very dynamic. Immediately from 20 amps to it's going to be 60 amps, again it's going to be 40 amps, and go on, so on. You can see the graph is going to be very different and dynamic compared to energy storage application. That's why it is used in consumer electronics, not in electric vehicle. Because in power banks or any other applications, the current delivery is not going to be this dynamic. So because of this, you can't just measure the battery pack with voltage, and you can't say how much estimated percentage of the charge is left in the battery pack. So because of this, that's why people are still using in some vehicles in India, like Hero and Kinetic and so on, which is not accurate. If you go for Ather and other scooties, people are using other technique, something called coulomb counting. So coulomb counting is nothing but let's say that you have a water bottle, and you know the capacity of the water bottle, 1 liter, and you know how much water is there inside it. And if you're just pouring the water out of the bottle, and if you're calculating how much water is being uh, flowing out of the bottle, and you can easily calculate how much is left in the bottle. So similar way, we're going to calculate how much current is being discharged and charged in this discharge. So in this case, we know the capacity of the battery pack, and how much charge of the current is being discharged. We know. With respect to that, we're going to calculate the overall charge left in the battery pack. Ultimately, all these things are having challenges. It's all not accurate, right? So because of that, what people are still trying to do is that there is something called SOH measurement using the impedance matching. SOH is basically state of health measurement, and the second one is that Kalman filter, external Kalman filter for SOC estimation. I'm going a little fast in this particular topic, but as the time is less, uh, these are the two important topics which is still in research areas where people can still dive in deep and can understand how it can be implemented and so on. Let's assume why this is because even in coulomb counting, the cell capacity will degrade with respect to the cycle of the cell. Let's say that you're using a cell for more than 5 years, then or 2 years or something like that. Then after 1 year, the capacity will decrease. So you don't know how much is decreased, right? So in that case, you just imagine. So with that particular capacity, only we estimated how much charge is left in the particular battery, right? So if the capacity, even if we don't know just the capacity itself of the bottle or the battery pack, we can't estimate the exact SOC to over the time. So because of this, what's happening is that we can't accurately define the state of charge. So what we're going to do is that we're also going to measure the health of the battery pack with respect to the time, how it is degrading and so on. So those particular thing is done using impedance matching. The second is external Kalman filter using for SOC estimation. All these things are very in-depth topic. I would like just to introduce this thing to you and to get in particular further in this particular topic. So coming to the fourth feature is communication to the external world. So as I said that communication is very important. Here we have multiple protocols widely used is CAN, RS-485, and LIN. I'll tell you why it is very important. For example, that India is very high rich in power electronics. Power electronics engineers are very high in India, but still the charger, electric vehicle charger is not made in India very easily. People are still struggling to figure it out and make it. The reason being is that the communication is what very important with charger and the BMS or any other outside system. So the charger should contain the communication part, the digital communication system. So that's all makes intelligent electric vehicle system. So the charger, the battery pack should be able to communicate with all other subsystems in the electric vehicle to ensure the safety of the overall. So that's why the communication to external world is important. And if you want to dive deeper, the CAN is widely used in car and other even scooties and so on. The secondly, RS-485 is used for diagnostic purpose. And the third one is LIN, which is used for buses and very high sophisticated systems. So, and I've almost completed the overall core features of the BMS. Now I'm just want to tell you how to choose the BMS we are ready-made buying. Just have to make sure that number of cells in series you have to, so that you can select the topology. Next is the cell chemistry. Cell chemistry is very important. What cell chemistry you're going to use, because and the third one is that what application you're going to use for. Let's say that you can't just use normal BMS for high level safety requirement applications. That for example, you can't just buy energy storage BMS to use for bus, so because the safety is not met over there. The fourth one is, as I said, like the safety level requirement. How much level of safety is required for that particular application, and then you choose that particular BMS. So I hope that the overall idea of battery management system is known for everyone and helped you to dive deeper into these topics further for your research or your design and development. Before I close, I wanted to share you with very powerful resources you can go through, and you can help your research or kickstart your research with these particular two links what I'm going to provide. These two links are by by Professor Ashok Junjunwala in IIT Madras. He's the professor. He's the person who actually brought in wireless communication in India through BSNL, and also he's the person who implemented all the ATMs, first ATM missions in all over the India with less than he reduced the triple X cost of the ATMs, and he implemented it in India. And now he's trying to implement the EV technology, and he contributed his almost 1 year in Delhi to implement the EV policy in government and so on. So I would highly suggest that to understand what is the overall opportunity in electric vehicles in India, and how the technologies innovation has to be happen in a little bit different way to adopt it in India, different way and so on. And as well as you can further explore in the second link for energy storage applications and so on. There are multiple resources you can go and get it. And if you wanted to contact me again, you can contact me through my email ID. And after this, I will share the particular PPT for this link, so you don't want to note it down right now. So finally, I believe that basic requirements is met, but still I just wanted to have a question and answer session. If you have any questions, you let me know. I'll clear it out in this particular session.
Yes, sir. Actually, there are. Thank you, sir, for your nice presentation. There are two questions actually.
Yes,
I just read it out. I just read it for you. The first one is, if the battery goes below 4.2 volt, will the generator will be on or not? Mr. Niranjan Kumar has asked this question.
Okay, so the battery is having something called nominal voltage and maximum voltage and minimum voltage. So the battery maximum voltage is nothing but 4.2 volt, the standard voltage for all lithium-ion cells. And certain chemistries have different voltages. For example, lithium phosphate, its maximum voltage is 3.8, 3.7. And lithium-ion voltage is 4.2, and its nominal voltage is 3.7, and minimum voltage is 2.1. So we can use only in between 2.1 voltage to 4 voltage. So these are the operating voltage. If we don't want to go beyond 4 or below 2.1, we have to operate in this particular region. So as you are asking below 4.2, that is actually is an operating region. So the overall application will run in a safe manner. If it is going beyond 4.1 or below 2.1, the overall system will stop functioning. It will go into fault condition unless until the fault is being recovered. Let's say if it is going below 2.1 voltage, the under voltage of particular battery pack will be raised, and the overall generator won't function. At that point, what we have to do is we have to charge the particular battery pack. Once it goes beyond the 2.1 volt of that particular cell, then when the fault comes to normal condition, then the battery pack is ready to function normally. Immediately it will work with the generator.
Okay, sir. Thank you, sir. The next question is, what about the power rating as a result of cell balancing? This has been asked by Dr. S. Kudaloli, sir.
Can you repeat the question now?
What about the power rating as a result of cell balancing?
Okay, I believe that you're asking that how much power is dissipated in the cell balancing.
Yes.
So the answer for that is that most of the cases, the maximum amount of current is being depleted through passive balancing is around 150 to 200 milliamps per each cell maximum, and for smaller applications around 80 milliamps and so on. And in this case, the power dissipation is going to be very less, and it's very negligible. It's not going to affect the overall system. And the second point is that you might ask, how are you going to decide whether it's 80 milliamps or 100 milliamps or whatever the current is going to be? It's a very complex question because let's assume that it has multiple parameters has to be checked to select a particular balancing current for each for all the cells. For example, let's say that you have a system and let's say you have electric cycle, and your electric cycle have 5 cells, and you're going to use electric cells. You're going to use the cycle for every single night, every day, and you're going to use that particular battery pack, going to charge the battery pack every night, and that means you have 8 hours to charge the battery pack. And I forgot to mention that the cell balancing only happens only when the charging and in ideal situation. So you're going to take into the parameter how much ideal condition you're going to have and how much charging time you're going to have for your battery throughout your application life cycle. And then you're going to decide how much charge current. Let's say that you have only less ideal situation and less charging time, then your balancing current you can increase into high to make sure that the balancing is happening in a less time. Or let's say that you have very high amount of time for ideal condition or charging time. Let's say you have whole night for charging your application. That means you can reduce the cell balancing current to the less. So that means that it can balance for a very long time, and it doesn't matter. You can reduce the cell balancing current less. So the power dissipation is going to be less at that particular point, and the heat dissipation is going to be less. So there are multiple parameters involved in this particular scenario. I am just giving you the basic idea how it is selected, the balancing current, and how the power dissipation is related to that particular scenario.
Oh, okay, sir. Thank you very much, sir. You have given a very detailed explanation for each and every question. Thank you very much, sir. I now invite Professor Dr. Usharani ma'am to give vote of thanks.
Thank you, Mr. Akilan, for a wonderful presentation and informative, useful for the research scholars and those who are doing research in a particular area of battery management system, especially for lithium-ion batteries. Thank you very much. You have spent your valuable time for us. Thank you all participants. Kindly have you put all your feedback swap today. I request all the participants kindly fill up today's feedback link. We have posted a chat box. Kindly fill up.
Thank you so much, ma'am. It's my pleasure that to be participating in this and share my knowledge which I have accumulated in.
Akilan sir.
Yes, ma'am.
you would have not noticed some of the feedback from the chat box. I just want to say some notes from that. Great
Okay, ma'am.
presentation style and talk about examples which all made for a really informative. This has more than met my expectation. Thank you, said one of the participants like this. And another participant said, very nice presentation. All contents were in research perspective. Good one. So everyone told here in the chat box that you have given very nice presentation. Thank you very much for this session, sir.
Thank you so much, ma'am. I'm glad that everyone is happy and hope they would have got a very good understanding. And
Yes, sir.
I
Very
hope
useful
that everyone is
information
going.
you have given for those who are doing research, battery management system. You given very elaborate description of each title. Thank you very much.
Thank you, ma'am. Thank you so much, ma'am. And
Thank you, sir.
thank you so much. Yes, ma'am.
Karkoli ma'am.
Yes, sir.
Vinita
Yes,
ma'am is
ma'am.
there, ma'am. Vinita ma'am
Yes,
is there.
Tell me, ma'am.
Vinita, kindly check whether all the participants have posted the feedback, ma'am. Have filled up. How many comes for you? Kindly check.
Dear participant, please fill the feedback and left the meeting, please.
For day 2, we'll put another feedback form, ma'am.
Where you send the feedback, madam?
No, feedback link is available in chat box. Kindly fill up your chat box for today's session.
So today's session, there is a feedback link is given, sir. I'll post it again.
Madam, we are not get the feedback link till now.
No, I'll post
In
again,
the
sir.
chat box, it's available, sir. Again.
Now I posted, sir. Please.
Where I get it?
So now posted here.
Sir, in
Can you check?
chat box.
It is
It is not in chat box, ma'am.
Sir, please see it.
So, the right side corner one
Mobile
box
application where it is there?
circle. That is the chat box.
Madam, in mobile application it is not.
Okay. Then please give your mail ID, sir. I will note it down. You send your mail ID.
No, ma'am, we are not getting the feedback.
Okay, sir. I will send it.
Can you send the ladies? In feedback from send to mail ID?
We will send, sir.
Yes, sir. We will send, sir. We note down your mail ID, sir. We'll send it to that.
Up to this time, we are not getting the feedback.
We have posted in the chat box, sir.
He is able to see.
We are using mobile phone.
Okay, sir. We'll post, sir. You just send your mail ID in chat box. We'll note it down, sir. Yes, ma'am.
Hello.
Yes, ma'am.
Ma'am.
Madam, in Google Meet it is not available, madam. Feedback link is not available.
Chat box only it is available, sir. In chat box.
Where it is?
Yes, sir. Kindly send your through the mail, sir. Kindly send the message that you are not finding the feedback link. I'll send you again to you alone.